Hi everybody, I'm Eli Uriegas. I'm an engineering manager at Meta. Currently I support the PyTorch Developer Infrastructure team, and this talk is kind of centered around what's new for PyTorch Developer Infrastructure. It's a generic talk. We didn't really know what to talk about when we first submitted it, so we kind of submitted it like this. And so I hope you guys enjoy all the different topics we want to hit on. So, first and foremost, I want to introduce the PyTorch Developer Infrastructure team. There's a couple of members of the team here today. This is at an offsite that we had recently where we got to actually meet in person for the very first time after working together. I think we formed the team around 4 years ago. So our first time ever meeting in person all together. So really, really awesome. So what is the mission for developer infrastructure? So our mission has kind of changed over the past couple of years, so I just wanted to kind of highlight the kinds of things that we tried to do for 2022, 2023, and looking ahead. So first and foremost, 2022 was a year about achieving stability. We wanted to get to green CI with kind of state-of-the-art flaky test detection and disablement. We find that when developers trust CI, it makes it a lot easier to kind of push changes quickly. On top of that, for 2023, our focus was really on going faster. So how can we provide quicker time to signal through things like target determination? And then moving forward, we're looking into how we can integrate generative AI, things like large language models, into our tooling for better debugging and triaging. Before I go into tooling that we've built over the past couple of years, I kind of wanted to go over some high-level goals and how we build our tooling in the first place. So first and foremost, we want to have a high confidence and trust in our testing infrastructure. What we find is when people trust the signal that's getting to them as developers, they'll likely be able to push changes without having to worry about actually causing regressions. As well, we wanted to have easy-to-use tools that provide visibility and stability. So when you're able to actually identify where a failure comes from, you'll be able to more likely debug and be able to fix it. And at the end of the day, we also wanted to maintain high velocity with reusable components. So with our tooling, what we always find is that we end up having components that we can reuse in a lot of other places. And so we end up doing that first and foremost. So building things out with that kind of in mind. And at the end of the day, this all kind of coalesces into increasing developer productivity, so ensuring that we can ship the best things at the right pace with the certainty that they won't break anything, ideally. So to go over some of the tools that we've built over the past couple of years, hud.pytorch.org is kind of our flagship tool. This is the one where all developers of PyTorch can actually go see signal as it occurs on the repository. This particular view is a timeline view of all of the commits on PyTorch main, and it kind of highlights failures as they come along. The on-call for PyTorch actually ends up utilizing this tool to be able to tell when failures start to occur and if a revert actually needs to go on. We also built out a view for people when they submit a pull request to actually be able to find signal quicker. What we found is that through different tools like CircleCI or GitHub Actions, they didn't always provide the right amount of context for failures, and we wanted to be able to provide a kind of unique experience for PyTorch developers so that they can get the quickest signal the fastest way. As well, on top of that, we collect, I want to say, probably the most amount of metrics of any open source project right now when it comes to CI signal. Basically, every interaction that you have with GitHub on the PyTorch organization, we collect the data for that. And so we just have a large data store where you can run all kinds of queries on top of it and be able to kind of extract a lot of information. And we basically make almost every decision off of that data. And we also have a dashboard. By the way, everything here that you see is open source. You can view it on github.com/pytorch/testinfra. So it's all there. Another thing that we built out that we thought actually really ushered in a new age of PyTorch developer productivity is at PyTorch bot merge. Essentially what it is we wanted people to be able to merge on GitHub. For historical context, the way that PyTorch was traditionally developed was by merging code in through the Facebook monorepo, and that code would get reflected back out on GitHub. Last year, we went on a big project to kind of change our development model to be able to merge on GitHub first and then be able to ship those features into the Facebook monorepo afterwards. And so essentially, we called the project GitHub First because you merge on GitHub first. And a lot of things came with this as well. So when you actually submit at PyTorch bot merge here, What goes on in the background is it spawns a workflow that runs a script that'll actually do things like merge on green, and it'll actually do some higher level things like do flaky test detection and just ignoring a flaky test and workflows as they occur. Which leads me to my next thing, which is flaky test detection and disablement. This is one of the things that we've built over the past couple of years. We understand that flaky tests are kind of the bane of almost every organization's existence. What we wanted to do is we wanted to have a system where if there was a flaky test that was detected on main of the PyTorch repository, we didn't want that failure to kind of propagate to every single pull request as it came through. So what we did is we built a system where we actually have a bot that will detect flaky tests on main or on pull requests, submit an issue to actually disable them, and then it will be globally disabled across every single pull request, across every single commit that's running at that time, and will not affect the people's ability to be able to land and merge and get good green signal, if they have it. 3 more things that I really want to talk about for developer infrastructure that are like super important to us. OSS-CI infra is the beating heart of almost all the things that we do. Every single job runs on a cluster of about 3,500 nodes at peak times that contains a large list of hardware, a large list of operating systems. We basically support all major operating systems. We support all of the NVIDIA GPUs. We support AMD GPUs. We're looking to support other GPUs as well as they come on board. So OSS-CI infra is a way that we can kind of meet the needs of the growing AI community and be able to test on all the platforms that are important to everybody here. As well, we built a bunch of reusable workflow components over the past year. We have an understanding that machine learning researchers aren't always the best at writing CI, and CI guys aren't the best at writing machine learning research. And so what we wanted to do is we wanted to be able to give people reusable components in the form of GitHub Actions workflows, where they can write something as simple as a bash script that sets up a GPU that allows you to kind of get access to the hardware that you need, and you don't have to think too much about how it gets set up. As well, we provide a ton of nightly binaries, and we do a ton of validation on those binaries in order to be able to actually ensure that when you receive a binary from PyTorch, it's actually what you would expect it to be. So to talk about that, I'm going to invite Omkar, who's also on the developer infrastructure team, to speak about that.
Cool. Thanks, Eli. So yeah, everybody, I'm Omkar. I'm a software engineer at Meta, also on the PyTorch Dev Infra team. Before Dev Infra, I worked on PyTorch Distributed with some friends here. But yeah, I think Eli kind of described a bunch of tools that we build to make the developer experience on PyTorch better. Another big part of Dev Infra is getting a healthy, correct, and performant version of PyTorch in the hands of our users. And this is done by our release infra. And we actually release at pretty large scale. So on any given day, we probably run around over 500 build, test, and upload workflows. And that number is large because we support a pretty sweeping build matrix. We have to build both wheels and conda binaries across different Python versions, CUDA versions, ROCm for AMD GPU support, different operating systems, different CPU architectures, etc. And we don't just do this for the main PyTorch core repo, but on the order of 10 other projects in the PyTorch ecosystem. So extrapolated to over the entire year, we're publishing around 200,000 PyTorch binaries. So in the past, we had a lot of duplicated logic across all of these different projects. We didn't have any standardization in terms of the platforms that they need to support. And this made actual official releases really difficult. So we decided to change that. And we created these modular reusable workflows built on top of GitHub Actions. And really the purpose here is that we wanted any project in PyTorch, whether existing or new, to kind of get up and running with their CI/CD in about 20 lines of config code. So all they have to do is kind of interact with this interface. It'll set up a clean build environment for you into whatever platforms you opt into, build the binary. It supported a number of hooks for custom pre or post build steps that you might want to run specific to your particular project. You can run any arbitrary smoke testing to validate the health of your binary. And with just this, any new library can start publishing binaries. They can be compliant with the entire PyTorch ecosystem, and they basically have a hands-free process for running not just their nightly build process, but also their official releases. So this is all the interface that a project maintainer has to interface with, but what really happens under the hood? So we have a nightly cron trigger, and what that does is it takes all the commits made to the project over the course of the past day, squashes them into one commit, and pushes that to the nightly branch of the project. This triggers a number of workflows, and each project has the flexibility to opt into which workflows they want to support. So at this level, we support wheels and conda binaries across Linux, Mac, Mac M1, and Windows jobs. And we also have some early support for Linux ARM64 wheels and iOS and Android binaries. So once these jobs are triggered, the first thing they do is they kick off this matrix generation job. And this matrix generation job essentially specifies the subjobs according to the Python versions and CUDA and ROCm versions that each of these platforms need to support. So these subjobs are all kicked off, and then they're dispatched to our self-hosted AWS cluster using GitHub Actions. And so each of these subjobs also contain their own kind of unique hardware requirements. For example, the CUDA build jobs will require some GPU instance, Windows build jobs will require a Windows instance, and so on. So our self-hosted cluster supports all of these different SKUs. And this is the same logical cluster that we use to run all of our CI jobs on, as well as all of our benchmarking jobs across the entire ecosystem. Each of the machines in here comes pre-configured with our custom AMIs where appropriate. For Linux jobs, we build custom Docker images, and all the build testing and uploading happens inside of those containers. So at this point, you have your build environment set up. You run your build. You do any testing that you want to do. And then for conda binaries, we upload them to our PyTorch Nightly Anaconda channel. And for wheels, we upload this to our self-hosted PyPy index, which is backed by S3 on the same AWS cluster. And this is the backend for the download.pytorch.org site that you can access. And so that is all just what happens for one project in the ecosystem. We actually have to do this for each project. And it also needs to be dependency aware because, for example, Torch Vision nightlies for a particular day will depend on PyTorch nightlies for that same day. So we can only start building Torch Vision once PyTorch nightly is build tested and uploaded. So we do this dependency aware staggering across the entire ecosystem. Everything gets uploaded. And after that, we fetch them all in for some ecosystem-wide validation workflows to ensure that all these binaries work well together, and we run some metadata checks as well. So yeah, that's the story of how PyTorch binaries are essentially built and distributed to all our users. Usually with a pretty high success rate, as Eli mentioned, we track all of this data. So if anything goes wrong, we're constantly figuring out where those issues were. And if anything does seep through all of these lines of defense, there'll probably be a GitHub issue within 5 minutes from somebody in this room, maybe. I don't know. So yeah, that's the story of release. And so this is all great, right? We have tooling to make development on a rather large and complex project easier. We have well-defined systems for CI/CD. We have significant automation to get PyTorch to our users. So what's next for us? There's been a lot of activity and research around large language models for software engineering applications. At the PyTorch conference, we introduced a lot of new tools and features for where PyTorch is enabling innovation in large language models. So we're thinking of how we can close the loop and use LLMs to improve PyTorch, in particular, the development of PyTorch. So there's plenty of interesting data that we have organically around not just the code itself, but commits, logs, metadata, etc. There's a large body of research, including models like CodeLlama, built by some friends at FAIR in Meta, where they're performant on things like code completion and multi-line infilling. A lot of these models are small enough to be able to be inferenced on a single GPU. and can easily be fine-tuned on specific downstream tasks. So we can use this data and these fine-tuned LLMs to, at the end of the day, provide an improved developer experience for PyTorch developers. So let me share some numbers to motivate a specific problem that we have. On PyTorch CI, to any push to a PyTorch PR, we run around 2.3 million tests. And that's a massive number. And it takes 4 hours for any developer to get full signal on any change they've made to PyTorch, which is pretty bad. And this really affects the developer experience, the speed at which you can iterate on your changes to PyTorch. And if we extrapolate that over the course of the entire year, we're running around 1 trillion tests on PyTorch CI in the entire year, right? And that comes out of somebody's budget. So intuitively, most changes don't affect all the unit tests being run, right? And all of these unit tests are repeated across this entire build matrix that we support. So it's clear that we're overrunning tests. We thought, how can we take some information from the code being changed in the PR to run only the most relevant tests? And this process is known as target determination in many build systems. It turns out that the PyTorch architecture is good for developer usage, good for building new features and things like that, but it's pretty bad for traditional target determination. There's lots of complex interdependencies between different modules, lots of Python code pybinded to C++, generated code, CUDA kernels, etc. And we've tried doing target determination with PyTorch in the past. We've tried hard-coded rules where if changes are only made to one module, don't run tests in a different module. We've tried explicit dependency graphs in the style of like the Buck or Bazel build systems. We've also tried some simple heuristics like past failure rates. And for one reason or another, we've all had to basically walk back these attempts. So we had this idea. Let's pose this as an information retrieval problem, right? We can take the traditional two-tower model approach as inspiration, which is a classic model that's used for many search applications. But instead of taking a user-supplied query and searching for the most relevant documents, we can take a code change and search for the most relevant unit tests. And so we employed the CodeLlama 7b Python model. We parse the AST of the PyTorch codebase, identify all the unit test functions and all the functions that they transitively call. And we use CodeLlama to generate embeddings for each of these test functions. And with this, we create an index of the unit tests. So when a new PR comes in, we can run similar AST parsing for the PR, find each function that's changed by the PR, use the same model to generate embeddings, and then compare the PR embeddings with the test embeddings using something like cosine similarity. So at the end of this process, which really mirrors the two-tower retrieval approach, we have essentially a ranked list of unit tests that are from most relevant to that PR to least relevant. And over time, we can get to a system where essentially we filter out the least relevant tests. And as we build kind of more confidence in this model, only run the most relevant tests. And the idea here is that the code embeddings will be most similar to test embeddings for relevant tests, and they will score higher. So we prototyped this, and the early results are really promising. We've tested this on a number of sample PRs. It's very good at detecting similar tests. The tests it flags as least relevant across a number of sample PRs are in fact completely unrelated. And indexing and retrieving after extensive optimization can be done in reasonable time bounds. So here's one sample PR that we tried this on. It made a change to Torch distributed FSDP, fully sharded data parallel. In fact, it changed the init function of that module. And so we find that the most relevant tests that the system identified were all FSDP tests. And the tests that it found as least relevant were in Onyx, JIT, FuncTorch, NameTensor, and other modules that had no interdependency or no connection to Torch distributed at all. So we're continuing to iterate on this to prune out irrelevant functions, adding context about transitive dependencies in the sequence that we encode, and potentially doing dimensionality reduction for the embeddings themselves. And we're working on rolling this out to run on PRs so that we gather data about like which kind of like where the gaps are in terms of this model, especially because there's no concrete benchmark to verify the performance. So I guess to tie this back into our overall like LLMs for developer tools vision, I think there's really two high-level things that we want to get out of this, right? As we continue to iterate on these models, we're going to find opportunities to both improve PyTorch as well as the upstream like inference code that we use. And the second thing is to do the actual kind of thing that the model does, which is to provide a better end-to-end developer experience for PyTorch devs. So for the first thing, right, we needed to do a significant amount of end-to-end optimization of the system to get it to perform well. So one of the things, we started off using Hugging Face to inference the Code Llama model. Because we're using this as a embedding model, we don't want the last layer activations. We actually want the second last layer activations, which gives us the actual embeddings. Hugging Face does not expose an API that lets us do this in a granular way. It actually gives us all the intermediate activations of the model, which can cause OOMs really easily. So we shifted to using the actual Code Llama inference code, which didn't support this. So we added support for essentially fine-grained, like being able to retrieve activations from any arbitrary intermediate layer. This still ran into out-of-memory issues on our A100 machine. And that's because the Code Llama inference code made the implicit assumption that we're using the model for next token generation. So it had this KV cache, right, which was mentioned in the previous talk. And so when you're using this as an embedding model, you're not actually calling the forward pass in a loop, so there's actually no purpose for having a KV cache. So we're working on upstreaming a change that enables a no KV cache option for using Code Llama or Llama 2 as an embedding model. And this is in addition to many other changes that we made for AST parsing and other parts of the system. We also see LLMs as only a part of the solution, but not necessarily the full solution. There's a body of interesting research work around looking at correlation between pairs of tests, whether they pass together or fail together with very high frequency, and other such heuristics that could be combined with the scores from our retrieval system. And we're exploring how we can best combine them to filter out the least relevant tests. And we have an additional set of use cases in the pipeline. For example, identifying the exact error line in large logs, where if you have a large number of tests or a very complex build like you do in the case of PyTorch, you might have like a multi-megabyte log file. Or for doing flakiness detection or error suppression, right? These things kind of prevent you from landing code into PyTorch. It prevents you from doing releases. So if we can kind of use the similar techniques to auto-detect when tests are flaky or when jobs are flaky, that would also be a very tangible quality of life improvement. And another thing we could possibly do in the pipeline is to do generation of unit tests. So we're looking at all these downstream applications. Again, the purpose is really twofold: to find opportunities to improve PyTorch and make it kind of a better tool for doing both training and inference for LLMs, as well as providing a superior developer experience for PyTorch developers. And yeah, with that, happy to take any questions.
Yeah, so having had this experience, it's like mind-blowing that you can use embeddings to deal with the tests. I hate tests, so that makes me really happy. But seeing what you've seen now, what do you think about starting a software project from scratch? And ideally, you want to avoid your test being a mess, but in this case, you say, don't worry about it. The model will take care of it, right? It'll figure everything out for us. Is that like a terrible idea, or could that be a plausible way forward?
Yeah, I feel like there's no good way of answering. But yeah, I think the difficult thing is as the project grows to an incredible scale, and I think we all have like firsthand experience with this, like as the number of commits scale to where you have like 1,000 commits a month, or have you an incredible number of tests, and folks kind of depend on every commit by commit being correct and being able to be built from source. You almost get to a point where you want to over-test so that you don't break people, and maybe you can clean up the mess around excessive CI time later. If we were building this up from scratch, like it is possible that maybe going the explicit dependency graph approach may have been better. But I think it's possible that that style of development might actually have made it harder to develop on PyTorch. And so maybe this like post factum way of cleaning things up is not bad. Yeah.
When will you be doing 3.12? Are you doing that yet?
Is this for like wheel support or for like torch compile support?
Model, you've got like 3 versions of Python. There's also specialized versions. There's like one that begins with an M, I can't think of, but it has specialized fixed C code inside of it so that it runs incredibly fast. It runs at C speeds, basically.
I see. 3.12, do you know?
We'll probably look to support 3.12 within the first release of the new year for 2024. That's probably the earliest that we'll be able to get it in. As far as alternative Python interpreters go, we probably won't support those, unfortunately. It's just a matter of like where we choose to spend our attention.
Yeah.
Thanks.
And and also to note there, 3.12 support for torch compile will always lag 3.12 compliant PyTorch binaries, because that's a significantly deeper integration that we need to do. Yeah. Yes.
Thank you for a great talk. I think it's a really novel way of using LLM to do this kind of test prediction. But one of my concerns is that like the result of the LLM output is sometimes kind of indeterministic. So for example, in traditional CI test loop, when I push a PR and get a test result, I have a sense of security that it's passing all the tests that it needed and it's going to work in production. But if you do the prediction, there always this kind of possibility where like some tests uncaptured by this similarity search. For example, like it happens very frequently, for example, in our company Databricks code base where we want to find something and something very far away, like doesn't seem to be related at all, is breaking. But for example, based on the similarity search approach, this test might not be detected, and people may complain to us after we merge a PR. So have you guys considered that part in your similarity search approach? And is there any like thoughts to address this to give, for example, develop a security where after we push the code, we know it's going to work after the custom test?
Yeah. So I guess there's 3 things that I can say to that, right? The first thing is that what the system gives us is a ranked list of tests, right? So we can determine some kind of threshold that we feel reasonable, right? We can be as conservative as only filter out like the last 10 tests, right? And then go from there in terms of like iteratively becoming more and more aggressive with filtering. So that's like a lever that we always have to tune in terms of like how many tests we want to filter out. After that, we basically run the entire test suite on the trunk of master all the time, right? So even if something is missed by a PR, everything will be run on the main branch. It'll go into that HUD-like system, and somebody will go and revert it if it broke something in those tests. So this is essentially a little bit of a trade-off. We might run like fewer tests on the PR. Maybe there's a slightly greater chance of you breaking something and getting reverted. But at the end of the day, we will make sure that trunk on a periodic basis is still healthy, right? And then the last thing to say to that is like we have that same issue, right? We have a monorepo as well. So we have this issue where we can merge something and something like many hops away because PyTorch has a massive blast radius. Might break, and then somebody comes after us saying like you've broken everything, everything is down, like please revert it. So we have the same issue, and to some extent, like at that massive scale, like you kind of just there's some amount of like proactive work that you do to ensure that enough reasonable testing is done ahead of time, and some amount of reactive work where you ensure that okay, if something breaks, you revert it quickly and keep trunk healthy, right? That's just a trade-off that needs to be done past a certain scale.
Yeah. To expand on his answer as well, for number 2, when we do trunk tests, we also do that as part of our land validation. So whenever you do at PyTorch.merge, it'll actually trigger a trunk test, which will include the full test suite before actually merging that in the main. So that's actually a prerequisite to moving into main is running a relay version of your PR against all of the tests that would normally run on trunk.
So it's
more like a signal, kind of seeing whether it's your PR is likely to work. And then before merging, we have a foolproof test before we actually merge it.
Basically. So yeah, target determination will probably mostly work at the PR test level, and then when we actually do land validation before we merge it into main, that'll be the full test.
I have a general question. So I come from a strongly typed language background, and so I had this experience where we had a big Ruby code base, which was dynamic language, and moved to Scala. Majority of tests were like checking is the number of parameters the right number. Are the types correct? So all of this goes away when you have a typed language. So I wonder, like in the PyTorch code base, what is the mix of C++ to Python, and like how many of these tests are basically because Python is dynamic language? If you, for instance, pepper everything with type hints, how many of these tests will go away? Is this a reasonable approach to decrease the number of tests?
Yeah. So I think over time the trend towards like being more Pythonic is the general trend of the PyTorch code base. The vast majority of tests are in Python, and target determination is only being run on Python tests at the moment. Typically, PyTorch unit tests or PyTorch tests are less unit tests and more integration tests. So they test things like, are the types right, less, and more of like, okay, if I run backward on a tensor with this shape, like, does it return the right inputs? Or, testing specific operations, testing whether process groups are initialized correctly, testing whether graph tracing is done correctly. The tests are typically more of that nature than, these like very common best unit test practices style tests.
To answer your second question around what the libraries we're moving more towards, I think Mark Sauerland had a really great talk as part of the keynote yesterday where he talked about PyTorch moving towards more Python code. I actually think 2023 was the first time the majority of the code in PyTorch was actually Python instead of C++. If you're aware of torch.compile, all of the backend stuff for torch.compile is actually written in Python. Yeah, at least that stuff. So, yeah, the basic idea being that moving PyTorch towards a more strongly typed language is probably not in the cards, at least in the near future. But it is something that people have talked about, and the typing thing is a very hotly debated topic, even amongst PyTorch corpus users. So, yeah.
Interesting.
Yeah.
How frequent you're building that embedding index that you use for the retrieval? So as people adding the new unit tests, how would you make sure you're not missing those things part of your embedding index?
Yeah, so I'm working on kind of this like selective re-indexing mechanism so that you can kind of like after PR is made to master, you can figure out like which tests were changed and only update those parts of the index. So basically like re-indexes selectively after each change to the code on master.
What if people introduce a new testing?
So so that will be covered by one of the heuristics, right? If you introduce a new unit test, that should be run no matter what on the PR.
Okay.
Yeah.
Then wouldn't that be expensive every time people adding few tests? You go and rebuild the whole embedding space, or is it an incremental type of thing?
So per PR, it'll be an incremental thing. And we actually, so after all the optimizations, we're able to build the entire index in 3 minutes for the entire code base from scratch. So the selective one will be significantly cheaper. Yeah.
Thank you, Omkar and Eli. This is great.